Alright, hi everyone. So now we're going to look at the more useful type of semiconductor, which is a doped semiconductor. So I want you to remember back to your chemistry for a moment, and we want to think about where silicon is on the periodic table. And it turns out that there are elements to the left and to the right of silicon. So phosphorus has one more valence electron than silicon, whereas boron has one fewer. So if we have a silicon crystal bonded to, each one bonded to 4 nearest neighbors, that means there's 2 electrons in each one of these chemical bonds between them, making 8 electrons in the so-called Lewis octet of that central silicon atom. So this silicon crystal will be charge neutral, and there's no free electrons. This would be the intrinsic case. Now what if we go in and we replace phosphorus in the place of one of those silicons? And it turns out that in a doped semiconductor, this is typically on the order of 1 out of every million atoms or so being replaced. So we've got all these bonding electrons satisfied, but then we've also got one more, because the phosphorus brought with it this one extra electron. And it turns out that this extra electron is free to roam around in the crystal and conduct electricity, meaning when you apply a voltage or an E field, that electron can move around, and we call it a free electron. That means it actually resides in the conduction band. So if we took a giant crystal of silicon and we put in one phosphorus per cubic centimeter, we would have Ni electrons, Ni electrons in the conduction band, Ni holes in the valence band, plus 1, because we put in just one phosphorus atom. And it turns out that that phosphorus atom introduces a quantum state which is very close to the conduction band edge. The ionization energy is very small, and we would call this a shallow dopant. So if we put in, let's say, 10 to the 16 of these, we would have Ni plus 10 to the 16. And because Ni is about 10 to the 10th in silicon, and that's 6 orders of magnitude smaller than the 10 to the 16 dopants we just put in, we can ignore the Ni part here. Now, consequently, because we've talked about how the Fermi level is unique and it's shared by both the electrons and holes, so in the valence band the situation is a little bit different. We'll talk about that in a moment. Let's look at the example of phosphorus quickly. So sort of doing the same exercise, you imagine an infinite crystal, and you're replacing 1 out of every million or so silicon atoms by a boron. And because boron has 1 fewer electrons than silicon does, it can't form one of these bonds. And in the case of boron, we have a hole which is free, and it can roam around the crystal and conduct electricity. That lack of electron or hole exists in the valence band, and these are called free holes. In terms of nomenclature, we have N-type which means that they're negative charge carriers. That's where the original N came from. And N-type dopants in silicon are things like phosphorus or arsenic, especially. And then P-type the boron is the most common, but aluminum and gallium are also sometimes used, especially in photovoltaic devices. And again, the N and the P refer to the charge of the charge carrier. And it does get a little confusing, I understand, when you say P-type, but then the element symbol P stands for phosphorus, which is actually an N-type dopant, so don't mess that up. There's a little section in the book that describes how to calculate the ionization energy of a shallow dopant in a semiconductor, and really what's happening is you're treating the problem as a Coulomb potential, so the 1 over R potential, and that's created by the extra. If you take out silicon and you replace it with phosphorus, you've added one more proton in the nucleus, and then you've also added this extra electron, and that electron will circulate around that proton, attracted by the electrostatic or Coulomb force. The only differences being that the mass of the electron should be given by m star, and the dielectric constant is not 1 as it is in vacuum, but instead it's something like 11 for silicon. So that system, again, let me refer back to it. Electron circulating around a proton is actually a hydrogen atom, and we've looked in our modern physics at the energy levels for electrons and hydrogen atoms, and we get the so-called Rydberg constant, negative 13.6 eV, divided by n squared, where n is the quantum level. And then we can do a couple of correction factors to get what should happen inside the semiconductor. It turns out that what we need to do is multiply by the effective mass, m star, over the electron mass, and then divide by 1 over the dielectric constant squared of the semiconductor. So roughly speaking, m star for electrons and holes in most semiconductors is roughly 10% or so of the free electron mass. So let's give that a factor of 10. And then the dielectric constant for semiconductors can range between, let's say, 7 and about 13 or 14 for most semiconductors. So basically there's another factor of 10 in the dielectric constant, and because it's squared, that means that we get the ionization energies basically on the order of 13.6 eV divided by 1,000, and this is for the n equals 1 state. So we're looking at transitions that take it from n equals 1 past all these other excited states all the way up, so it's ionized and free to roam around in the crystal away from the phosphorus atom. So this is the so-called shallow donor or shallow acceptor ionization energy, and basically what we're seeing here is that it's on the order of tens of milli-electron volts. And this is important because at room temperature it turns out that 26 milli-electron volts is the numerical value of kBt, so kB times 300, and that means that there's enough thermal energy to ionize these extra electrons or extra holes off of their dopant centers so that they can run around in the conduction band or the valence band. So there's some tables in the book that give some numerical values of the ionization energies for shallow dopants in silicon and gallium arsenide. And what's interesting is that for nice shallow dopants, it basically doesn't matter which dopant it is. It can be phosphorus or arsenic in silicon, or it can be selenium or tellurium inside gallium arsenide, and you'll get the same ionization energy because it fits this so-called hydrogenic model so well. Okay, so our next job now is to determine if we put in some number of dopants, how many will be in the conduction band or the valence band, depending on if it's n-type or p-type, and then also where is the Fermi energy. And then the last question is, if we put in n-type dopants, how many holes will we have left over? So the assumption we're going to make for shallow dopants and again we're talking about the extrinsically doped so the intrinsic case meant that there's very pure pure silicon, nothing else in it. Extrinsic means that there's something from the outside. Extrinsic means from the outside. So there's some phosphorus put in it or some boron put in it to provide electrons or holes respectively. So for shallow dopants at normal temperatures, like 300 Kelvin is room temperature, and then usually most devices operate at slightly elevated temperature. Although if you are ever working on, let's say, space missions where the satellite might actually be very cold, it might be approaching absolute zero even, then you have to think a little harder about these assumptions. But in the simplest case, the extrinsically doped semiconductor at room temperature or above, we can assume that there's a 1-to-1 ratio between the let's say the phosphorus concentration and the free electron concentration N. So every dopant gives one carrier. So what that means is if we go back to our I'm going to define one more term before I say that. The ND is going to be the number of donors, and NA is going to be our number density, number per cubic centimeter of acceptors. So if we go back to our expressions relating the Fermi energy and the free electron concentration, we can assume that for silicon doped with ND donors, we're going to have that equal to our N naught, which is our thermal equilibrium concentration, and that in turn is going to be equal to NC exponential to the minus EC minus EF over KBT. So we can we can quickly compute where the Fermi energy is from this equation. If we're given ND, we can solve for EF, and vice versa. Now, an interesting thing we can do also is transform the equation a little bit. So if we use the relationships, the expressions that we derive for Ni. So Ni related to EFi, we can write this N naught, which is going to be equal to ND, in a slightly different form. We can say it's Ni times exponential to the EF minus EFi, the intrinsic position, over KBT. So really what we're doing on a band diagram here, we have a certain number of electrons in the conduction band. This this EFi is it's uniquely defined by the band gap of the semiconductor, and we can say our EF is either measured from the conduction band edge, EC, down to EF. So that's the first expression here, referencing it to EC, or we can measure up from EFi. It turns out when we get into device physics and look at things like band bending later on in the course, the second expression here, reference to the intrinsic energy, is in many cases more useful because it allows you to directly compute built-in potentials. So now we know how to express the number of carriers you get when you put in a certain number of dopants, and that's under the simple assumption that there's one electron added for every n-type dopant and one hole added for every p-type dopant. You can then solve for the Fermi energies, and then we've looked at two ways to express the Fermi energies. Either referencing it to the conduction or valence band edge, and then the intrinsic Fermi energy. Now, the last part we want to look at here is sort of an interesting thing that happens. It turns out, we could go through some of this integral math and compute, if the Fermi energy is here, how many holes are left in the valence band. Because we've added donors, we've moved the Fermi energy up. But it turns out we don't really have to do that. So there's a very compact expression. It's really the expression of a rate equation, or a dynamic equilibrium equation, and it's simply that the product of electrons and holes in a semiconductor, whether it's intrinsic or whether it's doped, will always equal Ni squared. And it's kind of as its physical basis, what it says is, if you put lots of electrons into a semiconductor because you added phosphorus dopants, what is going to happen is it's going to increase the probability of electrons meeting with holes in the valence band and annihilating each other. And then there's a certain rate that electron-hole pairs get generated just by random thermal excitation. So the thermal energy is always picking up electrons and moving them across the band gap, putting them in the conduction band, but the collisions between electrons and holes resulting in annihilation are going at another rate. And this Ni squared, is an expression of this rate. So this is called the mass action law, and it is definitely related to thermochemistry if you've studied physical chemistry. So anyway, what this allows us to do is quickly compute the concentration of holes, for example, in an n-type semiconductor. So let's say we put in Nd donors. Well, then the number of holes can be easily calculated as Ni squared over Nd. So if we, let's assume Nd is 10 to the 16 per cubic centimeter, excuse me, in silicon. Remember that Ni is 10 to the 10th, so Ni squared is 10 to the 20th. We get 10 to the 20th over 10 to the 16th, and that leaves us with 10 to the 4th. So it's a very small but meaningful later on when we talk about devices, density of holes. So we're gonna add one more piece of nomenclature here. So the majority carriers. The majority carriers are going to be the ones that are intentionally doped or by the extrinsic doping. So if you have a n-type semiconductor, the majority carriers would be the negative electrons, and p-type, the carriers are positive and they are holes. And as you can probably guess, the other term, the minority carrier, is the other one. So the minority carriers in n-type are the holes, and in p-type, those are the electrons. And what this this minority carrier density becomes very important, especially when you're talking about transistors and optoelectronic devices. Okay, so we've gone over extrinsic doping. We've calculated the the relationships between the number of carriers and where the Fermi energy is. We've given two expressions for that relationship, either in terms of the effective density of states like NC or NV, or in terms of Ni, and then measuring energies off of measuring the position of the Fermi level relative to the intrinsic Fermi level.